In this video, we're going to look at these examples on page 3 of the 7-4 slides. The first example, an unbiased coin is tossed 6 times, and we want to know the probability that the coin will land heads exactly 3 times. Well, in this case, each outcome can be represented as a sequence of heads and tails, and using the generalized multiplication principle, we see that the number of outcomes of this experiment is given by 2 to the 6th, or 64. So we let E denote the event that the coin lands heads exactly 3 times. Sorry, that's better. Sorry, I'm a little obsessive about getting my my paper on the board right. So E is exactly 3 heads. There are 6 choose 3 ways of doing this. So that's 6 factorial over 3 factorial times 3 factorial, which is 6 times 5 times 4 times 3 factorial over 6 times 3 factorial, which is 20. So the probability is 20 over 64, which is 5 over 16 when we reduce that to lowest terms. The next problem here we go. 2 cards are selected at random without replacement from a well-shuffled deck of 52 playing cards. What is the probability first that they... Oh, I'm sorry. I'm looking at the wrong problem now. We want to go on to B. We want to know the probability that the coin will land heads at most 3 times. Okay, well, in that case, we are looking at some different possibilities. We're looking at the probability of 0 heads. Let's actually switch over here. Plus the probability of 1 head, plus the probability of 2 heads, plus the probability of 3 heads. Well, we already know the probability of 3 heads is 5/16. So we just have to figure out the other 4 here, or the other 3 here. The probability of 0 heads is 6 choose 0. Which is 6 factorial over 6 factorial times 0 factorial, so that's 1 over 64 there. The probability of 1 head is 6 choose 1, which is 6 factorial over 5 factorial times 1 factorial, so that's 6. 6 factorial divided by 5 factorial is just 6. So that's 6 over 64, or 3 over 32. I'm going to leave it in terms of 64ths here. And for the probability of getting exactly 2 heads, probability, I shouldn't be writing the probability of 2 is this, but the number we're looking for the numerators for each of these is 6 choose 0, 6 choose 1, and of course 6 choose 2. Okay, so that's going to be 6 factorial over 4 factorial times 2 factorial, which is 6 times 5 over 2, which is 15. 15 over 64. And we'll rewrite this as 20 factorial, 20 over 16, 64 again. And then we can add these up. And we get 1 plus 15 is 16. 16 plus 6 is 22. 22 plus 20 is 42 over 64. And we can reduce that by dividing both by 2 to 21 over 32. Note that we could write these as decimals pretty easily, just because when we divide something by a power of 2, we get something that that any number is divisible by to, however many decimal places. Next up. In our third problem, we're asked to find the probability that we get heads on the first and the last toss. Now, we're not saying anything about the other 4 tosses. We're just concerned about the heads on the first and last toss. Well, that's the probability that there is heads on the first toss. Times the probability that there's heads on the last toss. But the probability of getting heads on any single toss is 1/2. So 1/2 times 1/2, that is 1/4, and that is our probability of getting heads on the first and last toss. Moving on, back to that question I started to read before. 2 cards are selected at random without replacement from a well-shuffled deck of 52 playing cards. What is the probability, A, that they are both aces, and B, that neither of them is an ace? Well, there are, of course, 4 aces in a 52 card deck. It's just what I wrote over there. And we're looking for the probability that we draw 2 of those aces into draws. Well, that's going to be 4 over 52 times 3 over 51. Now, that is some pretty lousy probability there, but we can easily calculate that. I'll do it in decimals this time. I'll round it to say 4 decimal places. So that's 4 divided by 52 times 3 divided by 51 is approximately 0.0045. Now, the probability that neither of them is an ace, that's going to depend on, the first probability is 1 minus 4 over 52. And then we're going to multiply this probability that the first card is not an ace by the probability that the second card is not an ace. Okay, so our probability that the first card is not an ace is 1 minus the probability that it is an ace, which is 4 over 52. The probability that the second card is not an ace, so we can see that better now, is 1 minus 4 over 51. Okay, so that's going to come out to sorry. We've got 48 over 52 times 47 over 51. We could simplify that a little bit, but I'm just going to plug that into my calculator. And get to 4 decimal places, 0.8507. All right, moving on to this last problem on this page. A bin in the hi-fi department of Building 20, a bargain outlet, contains 100 blank DVDs, of which 10 are known to be defective. Why they didn't remove the known defective DVDs from the bin, we will never know. If a customer selects 6 of these DVDs at random, determine the probability, A, that 2 of them are defective, and B, that at least one of them is defective. Well, first we consider the probability that both are defective. And that's going to be probability that the first is defective, which is 10 out of 100, or 1 in 10, times the probability that the second one is defective. The second one is defective, given the first one is defective. Well, in this case, that's going to be 9 out of 99, because we've already taken away one of the defective disks and one of the total disks. Okay, so I can reduce that to 1 over 10 times 1 over 11, and that gives me 1 over 110, which is approximately 0.096. No, that's not right. The book doesn't like the way I'm doing this one, so we're going to change this up a little bit. Okay, so instead of doing it that way, my methods worked for the other problems, but this one we're going to do something a little different. We're going to do this as 10 choose 2. So we've got 10 disks that are good, and we're choosing 2 of them, times 90 choose 4 over 100 choose 6. That is, we want to pick 10 of the bad, 2 of the bad disks, 4 of the good disks, and 6 disks total. Okay, well, 10 choose 2, that's going to be 10 factorial over 8 factorial times 2 factorial times 90 factorial over 86 factorial times 4 factorial over 100 factorial over 94 factorial times 6 factorial. Okay, well, that simplifies things a bit. We're going to wind up with 10 times 9 over 2 times 90 times 89 times 87, 88 times 87. Divided by 4 factorial, which is 4 times 3 times 2, all over 100 times, I should have started that further over to the left, but we'll work with what we've got, 96 times 98, 99, 98, 97, 96, 95, over 6 factorial is 6 times 5 times 4 times 3 times 2. Okay, so we'll simplify as best we can here. 10 times 9 over 2, that's easy. That's 45. Times 90 times 89 times 88 times 87. Here we're going to have to do a little more work. I can divide 88 by 4 and 2, giving me an 8. And I can divide 90 by 3, giving me a 30. 30 times 89 times 8 times 87. I could also have divided my 87 by 3, but I went with the 90 instead. So then we've got 100 times 99 times 98 times 97 times 96 times 95 over 6 times 5 times 4 times 3 times 2 times 1 times 2. It doesn't matter if we include that one or not. So 96 is divisible by 6. 96 over 6 is 16. Um, 95, of course, is divisible by 5. If we do that, we're going to get a 19. 100 is divisible by, actually, we're going to do some more work with this, 16, because that 4 and that 2 can go in there, and we're left with just a 2 when we divide by those. And 100's a nice number to multiply by anyway. So that only leaves us our 3, which can go into our 99. So our 97 remains the same, 98 remains the same, 99 becomes 33, and then we've got 100. Okay, so that's 45 times 30 times, and I can do some simplification here too. Let's see, we've got a 5 in both 45 and 30. I can get 5s out of those and out of the 100. So that's 9 times 6. And we wind up with a 4 for our 100. There's a 3 in our 33 and in our 87. We'll use that. So 4 times 11 and our 87. 87 over 3 is 29. 98 is 2 times 49. I don't have any multiples of 7 here, so that doesn't matter too much, but we can get rid of the 2 at least. Leaving a 3 there. Okay, 89 is prime. We can't do anything with that. 8, of course, is a multiple of 4 and 2, so we can get rid of our 2 there and our 4 there, and get rid of our 8 entirely. So that leaves us with 97. 11 times 49 times 97 times 19 in our denominator. And I don't think there's anything else we can get rid of there. So we wind up with, did I divide my 88 by 8 and get 8? That should have been 11. Well, now I feel dumb. I'm going to redo this. Sorry. Okay, so we got 45. You know, it's probably easiest just to do this math without all this extra work. We're just going to do the multiplication once we've simplified our numerators and denominators. We've got 45 times, and let's see, we had the 90 over 2 gives us 45. 89 is prime. 88 over 4 is 22. And 87 over 4 is 29. over, and in our denominator, we have 100 times 33 times 19 times 97 times 2 times, or was it 98, not a, yeah, 98, there we go. Okay, so when we multiply this all out, our numerator becomes 45 times 45 times 89 times 22 times 29, which is 114,983,550 over I'm just going to grab these numbers from what I've got here. That's going to be a lot easier. This is approximately 0.096. That's our probability for this one. Sorry for all of the confusion. When we get into these big factorials, it gets a little awkward. So our last problem for this video involves we let E denote the event that none of the DVs selected is defective. We're looking for that probability. Oh, no, I'm sorry. At least one of them is defective. Well, at least one of them is defective. Means that there could be 1 or 2 or 3 or 4 or 5 or 6 that are defective, but there can't be 0 that are defective. So the probability is 1 minus the probability that none are defective. So what we do here is we calculate the probability that none is defective, and we subtract. So that's going to be the probability 90 choose 6 over 100 choose 6. Okay, well, 90 choose 6. Sorry, it's 1 minus 90 choose 6 over 100 choose 6. Okay, well, that 90 choose 6, that's 90. 1 minus 90 times 89 times 88 times 87 times 86 times 85 over 6 times 4 times 6 times 5 times 4 times 3 times 2 over 100 times 99 times 98 times 97 times 96 times 95 over, again, 6 times 5 times 4 times 3 times 2. And when we do all of this out, the probability that we don't get any is about 0.478. All right, that is it for this complicated video. If you have any questions, please get in touch.